Okay, hello everyone. So today we would be discussing assignment problems from the previous year's session based on the current week, that is week 7. So we are discussing assignment 7, which is based on some basic calculus. So this week, if you have watched the videos, you would have noticed that the videos are basically on some elementary topics in calculus like limits and derivatives. So those are the things that we would be discussing in this video, that is questions based on limits and derivatives. So let us begin with today's session. So before proceeding, as always, uh, I provide the relevant links to those of us who are joining for the first time. So if there are people who are joining for the first time, I'm not sure if anyone is over here who is here for the first time. Is there anyone out of these 6 students who are coming for the first time in this session? I don't think so. Anyway, so that's the link to the YouTube channel. I have put it up in the chat box. So the YouTube channel is where all these videos are recorded and uploaded, and it is also live streamed. So you can go ahead and watch previous week's session as well on the YouTube channel. And then we have the Google Drive link. So this is the Google Drive folder where all these lecture notes are uploaded. So you can go ahead and watch the videos again if you want, and you can also download the lecture notes if that helps you. So let us get started with today's session. This is on week 7, assignment 7, basic calculus. So the first question says the domain of the function fxy equal to cosine of x times y equals, and we need to select which is the correct option. Now domain, so if we define domain basically means the set of allowed input values, to the function. So if you have any given function, what are the allowed input values? Those will be the domain. Those will be forming the domain of that function. Now in our example, cosine function is defined for all real numbers. And because cosine function is defined for all real numbers, our domain would be R2. That's because x is also taking any real value and y is also taking any real value. That is, x belongs to R, y belongs to R. So x comma y belongs to an element in R2. So that's the domain of the function. Pretty simple question. If you want, we can discuss some other domain questions wherein you can think of simple examples where each value of the real number set may not be an allowed input value to the function. For example, let me just give you an example. Let us say if we have fx equal to tan x, then over here x belongs to all real numbers, that is minus infinity to plus infinity, except at n plus half pi. Okay, so basically tan x is defined for all values except at pi by 2, 3 pi by 2, 5 pi by 2, and so on. And similarly on the negative side, minus pi by 2, minus 3 pi by 2, and so on. Otherwise, it is defined on the entire real numbers. Next question, we need to find out the limit. So limit x tends to 0 of sine x squared plus x tan squared x over x squared. We need to find whether the limit exists or not, and if it exists, what is the value of the limit. Now, we can see, let us look at the numerator. In the numerator, x tends to 0 implies that the numerator goes to 0, and even for the denominator, x tends to 0 implies that the denominator goes to 0. So what we have over here is a 0 by 0 form, and because of that we will use L'Hopital's rule. L'Hopital's rule, which works for 0 by 0 form or the infinity by infinity form. So the L'Hopital's rule says that limit x tends to some value, say alpha, f of x over g of x is equal to limit x tends to alpha f prime of x over g prime of x. When this provided, you have this 0 by 0 form, that is limit x tends to alpha f of x is equal to 0, limit x tends to alpha g of x equals to 0, either 0 by 0 form or infinity over infinity form. So these are the two cases in which L'Hopital's rule works, and we have the first case, which is the 0 by 0 case. So let us apply this rule. So limit x tends to 0, sine x squared plus x tan squared x over x squared. This we will differentiate the numerator and denominator. So this is same as limit x tends to 0, derivative of the numerator. Now derivative of sine x squared, we will use chain rule. So that's cosine of x squared times 2x. Because sine x, the derivative is cos x, and derivative of x squared is 2x. So by chain rule, we have this. Then again, we will use chain rule and product rule. So derivative of x tan squared x is tan squared x plus x, and derivative of tan squared x is nothing but 2 tan x sec squared x divided by derivative of x squared is 2x. Now how we got this derivative of x tan squared x? That's like the product rule. So derivative of function 1 into function 2 is nothing but derivative of function 1 times function 2 plus derivative of function 2 times function 1. That's what we used. We used x as one function, tan squared as another function. So that's the derivative. So let us simplify. So we are separating out the terms. So 2x gets cancelled in numerator and denominator. So what we are left with is the following. Now, we will apply L'Hopital's rule again to this term right here. We see that this is again of the 0 by 0 form. because tan x goes to 0 when x goes to 0 and 2x also goes to 0 when x goes to 0. So again we will apply L'Hopital's rule. The first term plugging in 0 gives us 1, plus the second term we will apply L'Hopital's rule once again. So tan squared x, the derivative is 2 tan x sec squared x by chain rule, and 2x, the derivative is 2, 2 cancels out, plus now this third term is 0 because x tends to 0, tan x goes to 0 and sec squared x goes to 1. So the whole product goes to 0. So this gives me 1 plus 0 plus 0, which is equal to 1. The second term, this limit is also 0 because again tan x goes to 0 when x goes to 0 and sec squared x goes to 1 when x goes to 0. So the answer is B, that the limit exists and the value of the limit is equal to 1. Now you can think of cases wherein the limit may not exist. So there can be simple examples. Let me give you a few examples. Some examples in which the limit will not exist. So examples can be limit x tends to infinity of sine x. Why? Because this is an oscillating function. So it keeps oscillating between +1 and -1. So the limit is not defined when x tends to infinity. Another can be, another example can be limit x tends to 0 of the Heaviside step function. So Heaviside step function is the following. So that's the Heaviside step function, which takes the value 1 for positive x values and takes the value 0 for negative or 0. So in this case also limit is not defined because it's a discontinuous function. So these are some simple cases in which the limit may not be defined. So let us proceed. We are given two functions. Let g and h be two functions from real numbers to real numbers, and they are defined as gx equal to cos of x plus x squared and hx equals to x cubed. Then we are given a bunch of options and we need to see whether these options are either even or odd functions. So let me define what even and odd means. So even function is when f of x equal to f of negative x, and odd function is when f of, or I could write it, let's say the other way, that's better, f of negative x equal to f of x. So you typically know f of x, you want to find out what f of negative x is, and odd function is when f of negative x is negative of f of x. So that's the definition of even and odd. So let us look at gx. So this is even function. Why? Because cos x is even, then x squared is also even, and sum of even functions also gives you an even function. Then h of x equals to x cubed. This is an odd function. And what is g prime of x? G prime of x is negative sine x, cos x derivative is negative sine x. So negative sine x plus 2x. And this is also even. Why? Because negative sine x is odd 2x is odd, and sum of odd gives you even. So let us look at h prime of x. Are you able to see my screen?
Now we are not able to your print or anything.
Yeah, okay, just give me a second. I think something went off over here. Just give me a second, okay? Okay, can you see my screen now?
Yes.
Yeah, okay, fine. So yeah, so this is derivative of gx. So sorry, I think I wrote something wrong earlier. So this is odd. This is because this I was writing fine, that this is sin x is odd, 2x is odd, and sum of this is sum of two odd functions, not sum of two even functions, sum of two odd functions, and that gives you odd function. So if you add two odd functions, you get two odd functions. If you add two even functions, you get an even function. Now let us look at h prime of x. So h prime of x is what? It is 3x squared. So this is even function. So now let us look at the different combinations that we are given. So first combination is g prime x plus h of x. So that is negative sine x plus 2x, that's g prime, plus h of x is x cubed. Then we have gx plus hx. Gx plus hx is what? It is cosine of x plus x squared plus x cubed. Then next option is g prime x plus h prime x. So g prime plus h prime is negative sine x plus 2x plus 3x squared. And finally gx plus h prime x, that is equal to cosine of x plus x squared plus 3x squared. Okay, so this function is odd function. Odd. Why? Because it is sum of odd functions. Sin x, negative sin x is odd, 2x is odd, x cube is odd, sum of odd functions gives you odd. So the first one is odd. So this option A is incorrect. Option A says that g prime plus h is an even function. So that's incorrect. Then these two functions, these functions are neither odd. So they are neither odd nor even. Why? Because they are sum of odd and even. So if you add odd functions with even functions, you get a function which is neither odd nor even. So you see cos x is even, x squared is even, but x cube is odd. So that's why adding odd and even gives you neither odd nor even. Similarly, negative sin x is odd, 2x is odd, but 3x squared is even. So adding odd and even gives you neither odd nor even. And this function right here is even because it is sum of even functions. So cos x is even, x squared is even, 3x squared is even. So this whole thing is even. So the correct option is option D, which is g plus h prime is an even function. So let's proceed further. Now we have a question on finding the Jacobian. So let A denote the Jacobian matrix of the transformation given as x equal to u squared v plus v squared u, and y is equal to uv plus w, z is equal to uvw. Then we need to find out the Jacobian matrix and the sum of elements of the first row at the given point 1, 1, 3. So let us first define what the Jacobian matrix is. So Jacobian matrix is given as follows. Jacobian matrix is the matrix of any given transformation. So here we are transforming from UVW to XYZ. So that's the transformation matrix. So that's your Jacobian. For our case, let us find out. So del x by del u is nothing but 2 times uv plus v squared. Then del x by del v is u squared plus 2 times uv. Then del x by del w is 0. Then similarly, we will fill in the other terms. So that's del y by del w. So this is just finding out the derivatives. You are given the transformation and you simply find out the derivatives. So let me see if it is all correct. Let me just cross check once. So del x by del u, del x by del v, and del x by del w. Then del y by del u is v plus w, del y by del v. That should have been simply u, I think. This term, del y by del v is u, and del y by del w, that's also simply u. Sorry, I had written a little bit incorrect. So yeah, this is correct. Then del z by del u is vw, del z by del v is uw, del z by del w is ub. So that's the Jacobian matrix. And then we need to find out the value at this 1, 1, 3. So let us see. The first one is 2 plus 1, that's 3. Then again 1 plus 2, that's 3. Then 0. Then v plus w, that's 1 plus 3, that's 4. Then u, that's 1. U 1. V into w, that is 3. U into w is also 3. U into v is 1. So that's the Jacobian matrix at the given point 1, 1, 3. And then the sum of the elements in the first row, that's that. So in this case, the sum is 6. So this is the Jacobian matrix for U, V, W being equal to 1, 1, 3. And the sum of the elements in the first row is 6. Moving forward, trace of the Hessian matrix age of the function f goes. Okay, someone is asking some question before we proceed. Let me see. Why do we have a Jacobian matrix and a Jacobian as a determinant also? So that's a good question, Joshi. So Jacobian matrix is the matrix of the transformation that we have. So any kind of transformation you want to go, you would have a Jacobian matrix corresponding to that transformation. So that would be, let's say from polar to Cartesian coordinates you want to go. So the coordinate transformation is denoted by the Jacobian matrix. Now what is the determinant of the Jacobian? So the determinant is basically helpful when you are doing the coordinate transformation and you want to, let's say you have some integrals. Okay, so that determinant, so I can maybe write it somewhere, or maybe I can write it down in chat. So when you are, let's say you have some integral wherein you have dx and dy. So your integral is in terms of dx and dy, let us say that, and you are transforming into polar coordinates which are dr and d theta. So you want to go from xy, so you want to go from xy to r theta, let us say. So you would have a Jacobian matrix corresponding to that, and you have an area integral which is dx dy, and you want to convert it into dr d theta, and there would be some basically it's not just dx dy is equal to dr d theta. You don't have that. What do you have? You have dx dy equal to r dr d theta, right? If you remember from elementary school level calculus, so dx dy is equal to r dr d theta. So what that r is doing over there, that is essentially the Jacobian determinant that you are saying. So when you are transforming your integral from dx dy to dr d theta, it is not just integral dx dy is equal to integral r dr d theta. It is integral over dx dy is equivalent to integral over r dr d theta. So that r term comes from the, so that extra coefficient that you have, so that extra r in the in that term is basically due to the Jacobian determinant. So that's how the determinant is significant. And the Jacobian matrix is for any kind of transformation of the coordinates you are doing from xy, you want to go to r theta. So the coordinate transformation is there. For that you have the Jacobian matrix. And the determinant is when you are doing these kind of area transformations or volume transformations. So that is how you would do. Okay, fine. So now we can proceed further. So this question says that trace of the Hessian matrix, we need to find out the trace of the Hessian matrix for the transformation, for the function r going from r squared to r squared, where f of x, y, z is given by this big function over here, 3x squared plus 2y squared plus 5z squared minus xz minus 3yz. So this is, here we need to write down what the Hessian matrix is. Now Hessian matrix is related to the Jacobian matrix. It's quite similar in terms of its definition, just that in Hessian we deal with derivatives. So let me write down the Hessian matrix. So Hessian matrix is defined as follows. So this is the Hessian matrix. So that's your Hessian matrix. So now we can first find out the first derivative. So del f by del x is the following: del f by del y and del f by del z. Now we can write down the second derivative. So h is first term is del squared f by del x squared, so that gives me 6. Then del squared f by del x del y, that's 0. Similarly, you can fill in up the other terms. So that's del squared f by del x del z, -1. Del squared f by del y del x, that is 0. Del squared f by del y squared, that's 4. Then you have -3 del squared f by del y del z. Then del squared f by del z del x, -1. Del squared f by del z del y, -3. And del squared f by del z squared, that is 10. So trace of a matrix is nothing but sum of the diagonal elements. So you have trace is sum of diagonal elements, and that is equal to 20. So option C. Now we move. Now these are some questions on derivatives. So the directional derivative of the function going from R3 to R, and the function is given, and we need to find out its directional derivative in the direction of this vector A at the value Q. Now, before proceeding, we need to define what gradient is. So gradient is defined as follows. This is gradient of a function. So our gradient for the given function is as follows. So directional derivative along A is nothing but dot product of gradient and that direction. So this is 4 by 3 y squared minus 2 by 3 of 4xy plus z plus 1 by 3 of y plus 2z. Then directional derivative along A and at the point Q is the value of this dot product at the point Q. So it is 4 by 3 minus 2 by 3, 4 plus 0 plus 1 by 3, 1. It's minus 3 by 3, which is -1. So B is the correct option. Okay, some people are asking some questions. Direction of steepest descent means. So direction of steepest descent, in simple terms, as you can see, by the English words that are used, it is the direction in which maximum change is happening and the change is negative. That means you are moving from higher values to lower values. And if you basically, if I draw some diagram, let me draw some diagram over here. Let us discuss some of the doubts that people are having over here. So earlier someone had asked some doubt about Jacobian determinant, and to that I had said that if you have some multi-valued some integral over multivariables dx dy, then this goes to r dr d theta, and not just dr d theta. So this r term was basically corresponding to the Jacobian determinant. So this was one of the doubts. Now some people are asking, what does direction of steepest descent mean? So direction of steepest descent, let us say if I have, so this is something, so let me say I'm looking at a 1D function only. Let us say I have some function and let it be an asymmetric function. Okay, so let my function be something like this. Okay, and let us say I am at this point, at this maxima point. And clearly from this diagram you will be able to tell me that if I move, so this is x-axis, that if I move in positive x direction, then that's my direction of steepest descent, because this function is decreasing much rapidly, means its slope has a higher change. The slope is changing much more rapidly in the positive x direction as opposed to going in the negative x direction, where the slope is changing, it is decreasing, it is changing, but the rate of change of that slope is slower. And the function, so the direction in which your slope changes or your derivative changes or your gradient changes, that direction, sorry, the derivative is changing in whichever direction and maximum change in that direction in terms of magnitude. So that is your direction of steepest descent, and that is related. So in one direction you have something very simple, but when you are dealing with 2 or 3 dimensions, then that direction of steepest descent is given by your gradient. So when you find out the gradient, then you have the direction of steepest descent. So next question is, if you move in that direction, you will reach maxima, minima in least possible time. Oh, someone is trying to answer that question, I guess. Direction of, what is direction of steepest descent? Someone is trying to answer that if you move in that direction, you will reach that maxima, minima in least possible time. That can also be an intuitive way of seeing, but it need not lead to a maxima or minima per se. Because for example, in this case, you can think that 0 is your minima, because as x tends to infinity, your function is going to 0, and x tends to negative infinity, your function again goes to 0, and it is going to 0 faster in the positive x direction. So if you think in that terms, that you are taking less amount of time in going to reach the minima, but if you look at it, then strictly speaking, 0 is not minima, strictly speaking. That's because the function never really becomes 0. It always tends to 0, but it never becomes 0. So you can intuitively try to understand it in that sense, but strictly speaking, like putting it mathematically, this definition may not be the most correct definition. So Deepak, your intuitive understanding of steepest descent is fine, but mathematically, as you can see in this example, uh, it may not be the most correct thing. So yeah, let's move forward.
Hello.
Yeah.
Yeah, and so I again have a doubt here. So why it is tending to zero, right? Then how
Yeah.
do we define the minima for such kind of function?
So yeah, means you cannot really say that 0 is minima. So it is limit is going to 0, but it is never actually becoming 0. So this function means if you try and solve fx equals to 0 for this function, you will not be able to find any number for x. You can only say that when x tends to infinity, it is 0. Because if you look at some very large value, let us say if you want to focus in this region, I'm focusing in this region. If I want to zoom in, if I'm zooming in on that region, so this is mathematician's way of describing things. So mathematics needs to be absolutely 100% correct and precise. So if you zoom into this region, you see this kind of a function. So this is just zooming in, okay, zooming into that region. Now you see, if I am at this point, you would see that this point has a lower value than some point over here. But if you keep moving further, you are reaching lower and lower values. So you can't say that you can't say that this particular point is my minima, because well, this is what I'm looking at. No, if you move further, that's how infinity is a very strange thing. So if you move further, you get even lower. So if you keep on increasing x, your value keeps on decreasing, and you keep on going closer and closer to 0, but you never actually reach 0. So if you never actually reach 0, you can't say that 0 is your minima.
Okay, thank you. Yeah.
Yeah.
So can we say that this is the direction of this is the direction in which we get highest delta?
Yes. So highest delta means what? Highest change in your slope. So you have some slope at one point, and if you move in whichever direction, so if the magnitude of that slope is changing fastest, that is what you are calling as delta. So that is the direction in which you will say direction of steepest descent. So maximum delta is also same thing as seeing the change in slope, because slope is also defined in terms of delta, in terms of change in your values. So that is how mathematicians' way of describing things. But your intuitive understanding is perfectly fine. Means there is nothing wrong in your intuitive understanding of trying to reach minima in the least possible time. You can keep this intuitive understanding in your mind and proceed further. There is no harm in that. But you should remember that mathematically speaking, that is not necessarily the most accurate or correct definition. So fine, let us move forward. Yeah, we solved this question. We were on question number 7. So question number 7, we are given some functions f and g, and we need to find out the value of this expression over here. So it is very simple. Gradient of f is what? Is y plus z in the x cap direction or the I cap direction, then x plus z in the j cap direction, and y plus x in the k cap direction. That's gradient of f. Gradient of g, since I'm writing in component form, this is in the component form. So this is same thing as writing it like so. And then gradient of g, similarly we can find out that's gradient of G, and then gradient of F transpose gradient of G, that's taking the transpose of the first, that is the following. So transpose means to swap rows and columns. And that is simple. You just multiply this thing, first element with first element over here, second element with second element, third element with third element. So it's a dot product essentially. That's how you write dot product between vectors, and this is what you would get. And at the point P, so at P, this dot product between the gradients is the following. So 4 times -1 plus 1 plus -4 times 1 plus 1 plus 2 times -1 plus 1. So that's 4 into 0, -4 into 2 plus 2 into 0. So that's -8. So -8 is the correct answer. Moving further. So we are given some expression for W, X, Y, and Z. So W is some function of X, Y, and Z, and X, Y, and Z are some functions of T and S. Then we need to find out the value of derivative of W with respect to T at a particular point, S equal to 0, T equal to pi. So the differential, we will use the chain rule. So the differential derivative of W with respect to T is W with respect to X times X with respect to T plus W with respect to Y times derivative of Y with T plus derivative of W with respect to Z and derivative of Z with respect to T. So that is according to the chain rule. So del W by del X is Y and del X by del T is e to the power S times 2T. Similarly for the other terms. And then put in the value, put in the expression for Y, X, and Z in terms of T and S. So that's Y is T cos X. Then X is T squared e to the power S. And Z is S sine T. So that's that. Then del W over del T at S equal to 0, T equal to pi. This plugging in the values. So this is equal to 3 pi squared. Now we have this. So this is since someone was asking about Jacobian determinants. So here you have to find out the Jacobian determinant. So we have been given a transformation between x, y, z and u, v, w, and we need to find out the Jacobian determinant this time at a given value. So the Jacobian determinant, this is how it is denoted. So it is the determinant of the Jacobian matrix. So this Jacobian determinant that we were discussing, this is nothing but determinant of your Jacobian matrix. So let us find out these derivatives. So del u by del x, 1. So these are the derivatives. Del u by del x is 1. Del u by del y is 2y. Del u by del z is 3z squared. Del v by del x is yz. Del v by del y is xz. And del v by del z is xy. Then finally del w by del x is 2x. Del w by del y is minus z. And del w by del z is minus y. So at the given point, at the point x, y, z equal to 1, 1, 1, you have the following, just plugging in the values and then expanding the determinant along the first row. So this is negative 3. So B is the correct option. Finally, this is the last question. We are given that z is equal to a function of x and y, where x is some function of u v and alpha, and y is also function of u v and alpha. U and v, alpha is a constant. Then we need to find out fu squared plus fv squared. Now this is just a notation. You need to know these notations. So fu is nothing but del f by del u. So it's a shorthand notation. And by chain rule, this is del f by del x by del u, plus del f by del y by del u. So again, by using that shorthand notation, del f by del x is fx, and del x by del u is cos alpha. Del f by del y by shorthand notation is fy, and del y by del u is sin alpha. So fv is del f by del v, which is del f by del x by del v by chain rule. So now we need to find out fu squared plus fv squared. So fu squared plus fv squared, that's plain and simple algebra. Just expanding the terms. So this last cross terms cancel out, giving us fx squared plus fy squared, because cos squared alpha plus sin squared alpha is equal to 1. So the correct option is option A, that fu squared plus fv squared is equal to fx squared plus fy squared. So that's all for this week. This week was on basic concepts in calculus involving limits and derivatives and functions. So hopefully these problems will help you solve the current week's assignment problems. So that's all for today's session. And yeah, that's all.
Recording stopped.